So thank you all for coming out this morning. Today I'm going to be presenting to you the results of our group's latest research effort, which was to develop memory forensics techniques to let us automatically detect and analyze malware that monitors hardware devices. And if you work in the incident response field, you likely see this malware all the time. We see this targeted at our clients on a daily basis. And if you read the reports from other security vendors, it's pretty much universal that when you have a motivated threat group targeting an organization, whether that's a research group inside the organization, whether it's executives, whether it's down to just an individual person, the malware that gets deployed on those machines are going to leverage access to hardware devices for truly sensitive information. Everything that's typed on the keyboard, all of the activity with the mouse, you will see the microphones being sampled and then audio shipped out. The video cameras are going to be recorded, and whether that's still pictures or video that's produced off of it, all that gets sent back to those attackers. And so if you're an individual and you're targeted by a hostile foreign nation, their intelligence service, you probably don't want everything you do within 5 feet of your laptop shipped out to those people so that they can take advantage of it. And certainly if you're trying to keep secrets within your organization, having all of that monitored across your fleet is going to make that very difficult. And then, so what we wanted to do was get it to where our memory forensics algorithms, our tools like Volatility, could just automatically find these, rip these out of memory, and make it where attackers know if they're going to use these types of techniques, they're going to be caught rather quickly. But unfortunately, we knew from our existing work and our existing research that the algorithms that were present and available before our work were either outdated, so they didn't support things like Windows 10 or the latest Mac. They were incomplete, so we knew that malware could try variations on existing techniques that wouldn't be caught. And then some of them with the newer ways that malware works were just non-existent. So we could certainly figure these out on our own through reverse engineering and things like that. That's how we knew we were missing stuff. But we want to be able to automate things at scale, so we need to really understand how it works. So this turned into a pretty significant research project. It took us 2 to 3 months to get, with a lot of reverse engineering, source code analysis, get it working, but we wanted to do a very thorough job. So we started at the beginning by taking every malware report we had internally, as well as all the ones that we could get online. We made a list of the APIs and the subsystems that process malware will abuse to get access to the hardware devices. We then spent many, many nights and weekends in IDA Pro and other tools figuring out how those APIs are implemented on the system. We then developed proof of concept applications, so exactly what we saw the malware doing. We wanted to implement that on our own in a controlled manner, so we knew that our tools were working. We want to make it where we truly never miss this malware in the wild going forward. And then we're going to develop new volatility plugins so that, like I said, we can do this in an automated way. And if you're in this talk, you're probably interested in memory forensics or probably know what it means. But if you're not too familiar with it, the reason memory forensics is so important and we spend so much time working on it is when you look at modern attacks and modern threats, the payloads that are used, the tool sets that are launched, the really important parts, or in some case all the parts, are memory only. So what that means is nothing is written out to disk. If you reboot that machine, all your forensics evidence goes away. There's nothing to look at. And as you might imagine, all the data that's sent from the operators is encrypted on the network. So even if you're a place that has full PCAP, that doesn't really help, right? So we want to be able to get a sample of memory off a machine and then deeply analyze it to find this type of malware. And this type of malware, like I said, is used all the time. There's other black hat talks throughout the week where people are showing off their new memory-only frameworks and such. But this quote that I have at the bottom, or this screenshot that I have highlighted, it was perfect timing. This literally came out when I was going through the slides last week and I added it in. Microsoft essentially burned this company out of Australia that sells commercial spyware and is used by governments across the world. And it was really interesting. Microsoft just destroyed them, like reversed it down to every bit, all the capabilities it had. But in the beginning, you see what I have highlighted in red. All the capabilities of that tool set that they found and published on were memory only. So it was an example from literally a week ago. When you're targeted by motivated actors, you're going to get hit with memory only malware. So again, we looked at Windows, Linux, and Mac. We started with Windows because we figured it would take the longest to do. So that's what I'm going to go through first. We focused our research on Windows 10. This is what, I know not everyone updates right away and Windows XP lives on forever, but we do see Windows 10 in most of our investigations now. So we wanted to make sure our algorithms were up to date for that. So we went all the way back to the first stable versions of Windows 10 through the latest stable release back in March. We had our memory collection tools, so we could do our research and then also save out memory samples with those proof of concepts loaded, so that going forward, we know that our tools always work. The first API that we looked at that malware abuses is set Windows hook EX. This has been abused by malware for years and years on Windows. The idea of it and the reason it gets abused so much is it's extremely powerful. All your malware has to do is call one function. In most cases, when it calls that function, it's going to pass in the path to a DLL on disk that it wants injected into every process. And then the malware doesn't have to do anything after that. Windows does all the hard work of every time a process starts, that DLL gets loaded. Once an event is triggered, it does all the hard work of making sure the callback that DLL registers gets triggered, so every time a key is pressed, every time a mouse is moved, and so on. And so again, this makes it very nice for malware. If you're familiar with code injection with like create remote thread, virtual alloc EX, the malware doesn't have to do any of that. The operating system does it for it. So inside of Volatility, we have a plugin called Message Hooks that's been around for years and years, but it was never properly updated for Windows 10. And when we really studied the set Windows hook EX usages out in the wild, we realized there were some variations on it that we weren't detecting. And one of them that I'll talk about, I actually don't know anyone in the field who knew about it before. So it's something that wasn't known, but we want to detect all of it. So this is a look at set Windows hook EX, the parameters that the malware is going to set. The first one is you say which device you want to monitor, keyboard, mouse, and so on. And then the last two things that you have to send in are, in most cases, you're going to send the path to a DLL, but we'll see you don't have to do that. And then the last parameter, the thread ID, says if you want to monitor a specific thread, so basically if you want to monitor just one application, or if you want to hook all processes and applications for a specific user. And then again, you send in what you want to monitor, where your code is that's going to monitor it, and then Windows takes care of it for you. This is the proof of concept that we developed for this technique. You can see that we have a DLL called fakeDLL.DLL. We have a function that's going to get registered and called every time the mouse is used. We're calling set Windows hook EX with the path to that DLL. And for the last parameter, we're setting 0, which is the same thing as null. So this is going to affect every process on that user's desktop. At the bottom, what we're seeing is this is the memory sample that we have once our proof of concept was loaded. And the way it works is you launch this malware, and then from then on, anytime the mouse is moved in an application, in this case, the DLL is going to get loaded. So we ran a notepad, we opened a notepad instance, moved the mouse inside of it, took the memory sample, and as we would expect, that notepad process now has our DLL loaded by the operating system. But this isn't enough to automatically detect the malware. There's going to be dozens of DLLs in most processes, so you can't just look at a DLL list. We just do this here to make sure that our backdoor loaded correctly. Sorry. So to actually detect these hooks, we have to examine the GUI subsystem of Windows. As you might imagine, this is closed source. So when we say examine, it means lots of time reverse engineering the Win32k subsystem in the kernel. So at a very high level, when you log into a Windows system, that will create a session, which creates a Windows station. And then what you're used to is you use one or more desktops. The one on the local machine, you can RDP into a system. And associated with that desktops are two things we need to track down. The first one is the atom table, which is basically a set of strings associated with what's occurring on that desktop. In this case, there's going to be a string for the full path to the DLL used to implement the hook. And then you can see down in the bottom in the black box, there's the set of hooks. Remember, the name of the API is set Windows hook EX. So this is going to store information on all the applications that are monitoring that desktop. So like I said, initially the Message Hooks plugin was very inconsistent, in most cases produced no results against Windows 10. So the first thing we had to do was reverse out all the offsets for the different Windows 10 versions. But then we noticed that when we did that, we weren't getting the path to the DLL back. So remember, we have our hook, but to know which DLL is actually implementing it, we have to look in the atoms table. This was super frustrating because it worked on literally none of the samples that we created at first. So we were like, okay, we have to go back to the drawing board. Fast forward many hours in IDA Pro later, and this is what you're seeing on the bottom of the slide. So for every version of Windows, going back to XP, until before 10, you had this thing called the user atom table handle that was your table of strings. Volatility knew how to find it. And then starting in Windows 10, it looks like Microsoft just re-implemented that whole subsystem. So we had to go through an IDA, figure that out, and now we have this other table that we can inspect. So the message hooks plugin now branches, right? It knows if it's looking at Windows 7 or Windows 10, and we get those paths back. So now just by running the plugin, even on the latest versions of Windows 10, you get the DLL placing the hook, you get the offset inside of the DLL where that hook is, and if you're familiar with volatility, you can just extract it out at that point and start reversing it. The second variation of set Windows hook EX, and this is the one that is kind of mind-blowing, and like I said, once we figured out, I polled a bunch of people that I would consider experts in like Windows internals and malware. No one knew this was possible. So the idea is it only works for the low-level keyboard hook. So you're hooking the keyboard at the low level, you are going to get every keystroke, but when you call set Windows hook EX, you say, I'm not giving you a path to a DLL, but I still want to hook every process across the desktop, which makes literally no sense. So you call it like you see up the top here. You give the DLL that you reference is your own executable, which is obviously not something that can be injected into other processes. And we found this documentation. It wasn't incredibly easy to find, but we eventually found what you see at the bottom of the slide on the MSDN. And this is where it gets really crazy. So what Microsoft is saying is, if you want to have essentially keylog every process on the system, you don't have to put any code into those processes. You don't have to hook those processes at all. You just have your own process running, and then Microsoft or Windows is going to do all the hard work to send your code the keystrokes anyway. So if you're used to doing memory forensics or live forensics on a machine, you kind of understand if a process is being keylogged, if a process has malicious actions focused on it, you can extract the memory of that process, you can debug that process and find the malware. In this case, all of the processes that are being keylogged have literally zero anything you can look at. It's all in this other process on the system. So I don't know of anywhere else this happens. It's very strange. So we wanted to be able to make sure we could detect it. And this is something where volatility kind of had support before, like once we got it working on Windows 10, but the output was not particularly useful. So we're seeing 3 blocks of output here. You can see there's spaces between them. But the first one is the global information. So volatility is saying, hey, there's this low-level keyboard hook that's hooking every thread. It tells us the address of where that is, but it has no idea which process it's in, which is fairly useless, right? Say you have 50 processes on a desktop, you're not going to go to that address in 50 different processes and look for malicious code. So we went back to reversing for a while, and we figured out that on a per thread basis, which when I say thread, just think of process. So on a per thread basis, there's a flag that is set if that process set the hook. So what you're seeing in the second 2 blocks is for the PowerShell one, there's a false printed, and then for the GUI tester all process, there's a true printed. Message hooks didn't print that before. That's us parsing that flag to say, hey, there's a global hook. It's not PowerShell that set it. It's the GUI tester all, which you'll see quite a lot because that was our proof of concept application. So again, this was a really strange edge case. It's keylogging on the system, and memory forensics knew nothing about it before. Then the last variation of set Windows hook EX is, again, you pick whichever device you want to monitor. This one isn't limited to just the keyboard. You can send it either a path to a DLL, or you can send it null like before, but you're going to target a specific thread, which again is a process. So if you just want to keylog the web browser, the password manager, whatever it might be, you can pick that, and then you don't have your code going into every process. There was literally 0 documentation about this online. So again, it was more time in IDA Pro. So off of the threads, so what we saw on 2 slides ago where we saw PowerShell and GUI tester all, inside of the data structure in memory that represents that, there's another kind of per thread Atom table. Atom table is in quotes because it's not really a generic Atom table. It just stores the DLLs associated with that thread. But once we figured that out, we were able to update the plugin to then find this hook variation. So like I said before, this type of hook variation was not known to volatility at all. When we first got it working, when we figured out we had to go deeper into the thread, we have the output that you see up top, and the module 7, which is obviously not a path to a DLL. What that is saying is, I know that the index into the string table is 7, but I don't know how to find the string. So then we figured out about that per thread Atom table, and you can see the updated output at the bottom, which we're still able to recover the DLL path. So now, as far as we know, no matter how set Windows Hook EX is used to keylog systems, we can automatically find it. The second API on Windows that we looked at is called Register Raw Input Devices. This is another way to perform key logging. A lot of your EDR systems will look for calls to set Windows Hook EX. Obviously, they're not perfect, and I'm well aware that can be bypassed, but they do make an effort. So Malware started using this API instead to achieve essentially the same goals. When you call this API, there's some constants you need to use. So you basically just say, I want to hook everything, and I'm interested in the keyboard. It's a little different than just passing a path to a DLL, though, in this case. Instead, you tell it which window you want to target. So if you remember our picture from before, we got down to the desktop of the user, then we needed to look at the atom tables and the hooks to figure it out. This is a bit different. We're not reusing those same data structures. And then what you see at the bottom is part of our proof of concept code. We have our callback function, or our hooking function, which is called wndproc. We're calling register class and then create windows with that function associated. So what that means is every time a message is passed to that window, our function is going to be called. And once our keylogger is active, you might guess the message information is going to include the keys that were typed on the keyboard. So this is a partial part of our implementation of that callback function. You can see for WM create, when a window is created, we're going to say register raw input devices. So from then on, every time a window is created on the machine, you open Chrome, you create a new tab, any application creating windows, we're automatically going to get to hook it. And then when that window starts producing input, which again is someone typing on the keyboard, we can read out that key and log it or send it across the network. There was no memory forensic support for this before. So we figured out that off of those same data structures, we were getting the thread and process information. There was a second set of tables that we could examine, and it would tell us all the processes that had used that API. And then this is a brand new plugin called Raw Input Device Monitors that we wrote to implement what we were just talking about. And as you can see, it tells us on the desktop in the GUI tester all process, in our proof of concept, the name of the window was my hidden window, just so it would stand out in the output. We have the address where that hook is and the process ID. Again, we can extract that executable out of memory and then really start to figure out what happened. So we targeted those two functions for Windows. The next thing we looked at was Linux. We deal with Linux investigations all the time, especially in the cloud. And something we still see that works, which is rather unfortunate, is abuse of the debugging facilities. So on Linux, you have the ptrace facility. This is what lets processes do debugging on Linux. And then you have strace, which is a really popular tool to trace system calls that applications make. And if you're not familiar with system calls, anytime you want to interact with hardware, the network, another process, you have to make a system call to do it. So obviously, by monitoring system calls, you can monitor any hardware device, whether that's a keyboard, mic, video camera, and so on. You can completely disable this feature because it's such a security threat, but as you're probably aware, security patches aren't universally applied, people don't configure things right, so we still see this being abused in the wild. From a detection standpoint, there's two variations we wanted to be able to detect in our plugins with this. In this, what we're seeing is direct debugging. So if you start a process under a debugger, which in this case, we're starting the cat process under GDB. So cat is started under GDB, which is the debugger. You can see the process IDs are 778 and 780. And then we wrote a new plugin called Linux Process ptrace, which is going to tell you all the processes that are being debugged. And you can see in the output here, I have it highlighted. We get our GDB in our cat process. The flags for cat is ptraced, which tells you that it's being traced. And then you can see for GDB, it's tracing PID 780, which is cat. So we automatically report that interaction between the processes. Now, an extremely dangerous form we see of this quite often in the field is using the debug facilities to monitor the SSH daemon. So what we're seeing here is we're on a Linux system. The SSH daemon is running with PID 436. And then we're using strace, which obviously you have to be root, to debug that running SSH daemon. So we're not restarting the daemon. It's not like people who are currently logged in are going to get kicked out. We are just dynamically attaching to that running process. So once that was running in one terminal, I opened a second terminal and I SSH'd into that machine. And what you're seeing is me logging in. So the password was secret password ! That gets read directly by the debugger, because in order for the SSH process to communicate that information, it's going to go through a system call. So you steal the password right away. Then what you see is me typing the netstat command one letter at a time. That gets logged. You see where netstat is run. And then if you're familiar with how netstat works, it's going to read some files under procnet to figure out what connections are active and so on. So you can see how dangerous this is, right? If you use SSH keys, you'll get a little reprieve from it. But if you're logging with passwords and you have this type of malware, your passwords are getting logged in real time every time you log in, as well as all the commands you run. Now, making this infinitely worse is, you can imagine if ransomware automated this situation with using the passwords and then performing lateral movement. And then, still not good, but not as bad as ransomware, is in many environments you'll have to move through multiple Linux servers to get to your final destination. So you go through those jump boxes logging in each time. So you can imagine if box 1 is compromised with malware like this, and it gets the password that you logged in with. Then you go to box 2, which might be your internal credentials. The fact that you're logging into that remote machine is going to be key logged as well. And no matter how many hops you're using to try to be secure, the malware is just getting access to that data all along the way. So this is definitely something we want to be able to detect. So that same Linux process ptrace plugin we wrote to see GDB and cat interacting is going to work for this as well. If you remember, and it's in the first line of the plugin, our SSH daemon was PID 436. You can see it's listed here, and then it's ptraced and seized. You then see, I'm going to skip the strace process for a second. You then see more SSHD processes. Those are the children processes that are spawned to handle when someone logs in. And then once you successfully authenticate, bash or whichever shell you use will get spawned. And you can see that's being debugged also. So then if we look at the strace process, we see it's 1127, and the tracing column has all the PIDs that it's attacking, right, or that it's monitoring. And then if we have many SSH sessions going on, like on a real server, the amount of PIDs is just going to go on forever. And then just if you're not familiar with Linux, what seize means, it's actually really important in the output. That means a process was running and a debugger attached to it while it was still active, or when a process started, it's basically a victim from the start because its parent process was being debugged. So it's definitely something that we want to key in on. Another place we looked in Linux was input events. So this is a really handy feature for legitimate uses. It's pretty cool what it makes available, but it also gets abused by malware, just like everything else. So the way this works is if you look in the dev input bypath folder on a Linux machine where this is enabled, which if you have like Ubuntu, Debian, any normal distro, it's going to be there. And basically it makes a symlink file out to that physical device. So in this case, we can see that the keyboard is symlinked to event 0. And there's an API you can call that is, it's literally like 10 lines of code to read this device constantly and poll that device and then get anything sent to it, which it's the keyboard, so you're going to be sending keystrokes to it. So we wrote a new plugin to detect processes that were using this subsystem. It's called Linux input events, and you're seeing the output here. So one thing to be aware of is the login daemon from systemd is going to use this. That's legitimate, right? It's monitoring your keyboard so you can log into the system. So that's expected. But then we loaded, we didn't really write our own proof of concept for this one. There's a project called log keys on GitHub. That's like a proof of concept for abusing this subsystem. So we loaded that in our VM, got the memory sample, and then you can see we are reporting it. So in a real investigation, it would be as simple as filtering out the system daemon login process, which is, like I said, going to access your keys so you can log in, and then anything else is definitely suspect. The next thing we looked at is a feature of Linux that is just mind-blowingly painful from a security perspective. So I tried to highlight in the slide just how ridiculous this is. So the idea is you have an in and out control call, which is a subsystem. It exists on Windows and Mac and every other operating system where code running in an application can ask a driver to do something for it. Because you can imagine your process can't just go read the file system or send raw packets. So you can use this ability to ask the more privileged driver to do something for you. So for whatever reason, that doesn't make any sense. Linux has one of these requests that you can make that says, hey, for another terminal that's not mine, so someone else logged into the machine, I want to inject a character into their terminal's input stream, which translated from Linux terms means I want to fake keystrokes for them, which is like mind-blowingly crazy, right? So when you Google this, instead of getting any documentation on it, the first 10 links are about all the vulnerabilities that have been caused by this, all of the attacks that were propagated by this. And finally, OpenBSD removed it. So they didn't even try for backwards compatibility. If you make that call on OpenBSD, the call is going to fail. But the Linux developers refuse to do it. So especially in those shared environments, this is a major issue. And what's cool from a red team perspective is you can use this for a dead simple keylogger. What you're seeing on the left is the entire source code for our proof of concept. We wrote it in Python, so it's a little easier to understand. What you do is you open a handle to another user's terminal. You're then going to set raw on it, which means you want to deal with the raw characters going in. And then you're going to read from that terminal, right? So if you read from someone's terminal and they type a key, you're basically going to steal that key out. That would be bad because the user would notice they're typing and nothing's happening and nothing's showing up on the screen. So what you do is you read the latest character they typed, and then you use what you can see in the IOCTL call, the last thing that's highlighted in the red box. We're making that call to say, hey, take the character I just read and retype it for the user. So even if you're a super fast typer, you're not going to notice that your character is being stolen and replayed back and forth, but we can perfectly keylog all of their interactions through SSH or through a physical keyboard on a Linux machine. They're getting keylogged the whole time and they will never notice the difference. So again, we wanted to be able to detect this in an automated fashion. So we wrote a plugin called Linux TTY handles. And what we're seeing here is like I said, our proof of concepts in Python. So we're catching the Python process that's doing this, and the way our detection works, and you'll see it if you read the plugin source code, is we look at the console that our process was spawned on, so which user it was spawned for, and then we see if it has an open handle to another process. And at first we weren't sure, like maybe this would have false positives or something like that. We ran it over the couple hundred memory samples we had easy access to from the wild and everything. There wasn't one false positive, because why would you ever, legitimately want to spy on someone else's terminal? So it's a very nice indicator that something's wrong. And then I just ran the PSAUX plugin, which shows you the command line arguments, because again, for the process name, we're just seeing Python. But then if you look at the arguments, it's another project on GitHub called SSH Keylogger that abuses this facility. That one is kind of complex. We just broke down the functionality so it fit on a slide, but we're still keylogging there. And then the last thing we looked at was Mac. On Mac, you have what are called event taps. And what this means is you can tap the hardware devices. So you can tap the keyboard, tap the mouse, whatever it is you want to target. It's somewhat similar to set Windows Hookey X in that you tell it the function you want to be called when a key is pressed so that you can steal it. But this is built into Mac. There's a cool tool from Patrick Wardle, one of his free security tools, that will monitor the live system for when these are registered. So I run this on my laptop 24/7 because these are very dangerous. But we want to be able to detect it from the memory forensics perspective as well. For this proof of concept, we took another project from GitHub and modified it to work well in our environment. I have the link down here at the bottom to it. But what we're doing here is we're getting set up to call the create tap function. We're saying that we want to monitor the keyboard and that we want to monitor the flags. And the flags are important because that's going to tell you is caps lock on, is shift key being held down? Because if you're trying to steal credentials, you need to know that specific information. So once our event tap is created, we're going to add it to a run loop, which is a very technical part of Mac that just says, I want to hook every process. So just from this very simple code, our keylogger is going to be put into every process. That code will be placed into there, and then from then on, we'll get every keystroke possible. Now, reverse engineering this, what was summarized in like 2 minutes on that slide, was extremely difficult. One of the most painful reversing tasks I've taken on, because Mac works very differently than Windows or Linux. Mac, in its XNU kernel, tries to be like a microkernel. which if you're not familiar with that, says the kernel should only do the bare minimum. So what's in that privileged space that can access all the hardware should be very, very small. And this is good from a security perspective, but it makes memory forensics and reversing very strange because instead of being able to just look in the kernel and the process you're analyzing, you have to then go look at some other process that's actually doing the hard work. And there's no equivalent to that in any other operating system that we deal with. So after a good bit of reversing, we figured out that when you call the CG event tap create function, inside of your process is going to be the Skylight library. So that's what's going to implement a lot of the GUI stuff. And then we figured out that that eventually goes to CG place tap. And then inside the kernel, all that does, it's like 2 lines of code in IDA or just a few instructions. All it does is call Mac message inside the kernel with a hard-coded value. So you're reversing and you have literally no idea what that means. It's completely useless to look at that. So we had to figure out where is that actually reaching on the other end. So then we figured out in the Skylight library that for every _CG function, which is the one that the processes are going to call, so like the keyloggers are going to use, inside that same library is a companion function that starts with _x. And as soon as we figured that out, which was multiple days later, it was very easy to do it because you see the function that's being called and you see the handler. So with that, we wrote a plugin that can see these calls going into Windows Server. Once the Windows Server has that registered, then every time a key is pressed or the mouse is used, whatever it is that the malware was interested in, it's going to pass it back through the kernel, back to whichever process is doing the keylogger. So we then realized that was kind of interesting because there's 2 places we can look to find this type of malware. We can look inside the keylogger process. It's going to have the malicious function. It's going to have information on how it registered its hook. And then we can also look at the Windows Server process just to get a global list of all of the keyloggers. So instead of showing you assembly, I used the decompiler for a quick view. But we realized when we found the correct function, that x place tap, what happens is memory is allocated. I named it CGX event tap because we figured out that's what the data structure was when we were in IDA. And then you can see once that new data structure is created, it's pointed to a global variable called CGX event tap master list, and then that master list is getting pointed to the new tap. And if you're familiar with programming, that's how linked lists are set up. And the plugin was straightforward at that point. So we have a new plugin called Mac Event Taps. It looks inside of the Windows Server process. It finds this event tap master list, and then it just prints out all the entries. And this is another one where on a clean system, you shouldn't have any keyloggers active or things monitoring other hardware devices. Why would you? So you can see in this case, the plugin's reporting the fact that we found a keylogger, the PID, and then what it's looking for. So in conclusion, we did a pretty thorough analysis on all the malware that will monitor hardware devices and steal all the data. I mentioned it before, but if you came in late, and I think we were just kind of talking on the side, besides the slides where you have some pictures and some data, I think they publish tomorrow morning. You'll have a copy of these slides, as well as a white paper that turned out to be like 35 pages of all the IDA screenshots, all the really technical details. So if you want the full deep dive on anything I talked about, check out the white paper when it goes online. So thank you all for coming.